Well, hello to everyone participating in our seminar. My name is Jim McCurry. I'm a senior applications chemist with Agilent Technologies in the Wilmington, Delaware site in the US. Today, my topic is going to be helium carrier gas for GC and GCMS, conserving helium resources, or converting to hydrogen and nitrogen. So we'll be discussing both of these topics for dealing with issues of helium carrier gas. Now, the market situation with helium is not something that's new. It seems to be an ongoing issue every few years. And helium supplies are sometimes not reliable. There can be outages occasionally. And also, prices can increase. And that's prompted customers to look for alternatives to carrier gas for gas chromatography using something other than helium. We put together here a carrier gas decision tree. I'm not going to go through it in detail. Basically, it boils down to two things. One is if you need to continue to use helium for your carrier gas, particularly if you're using, say, GCMS methods, or if your SOPs will not allow you to change to an alternative carrier gas, you do have an option and you can use helium conservation. However, if you can take advantage of the opportunity to change carrier gases for your GC and GCMS systems, I'm going to discuss some of the approaches to migrating to either hydrogen or to nitrogen carrier gas for your systems. So first, let's discuss helium conservation. This is actually the easiest thing to talk about because it doesn't require any changes or revalidation of your methods because you'll continue to use helium as you always have. So if you really can't change or you don't want to change, the only choice you have dealing with reduced supplies of helium or increasing prices of helium is to try to conserve it. So there are a number of approaches to helium conservation. One of the most important ones does not even deal with the instrument or your methodologies. It's in fact looking at your infrastructure and doing maintenance and leak checking to be sure that you're delivering the helium to the instruments that you need without wasting it through leaks or problems with the infrastructure. So what you want to do is monitor leaks in your facility's helium delivery system. At our site, we have a central location where the helium is stored and then it's delivered throughout the building through the various plumbings and regulators that are in the building's infrastructure. This actually can have the greatest impact on helium savings. About 7 or 8 years ago, we noticed that we were using a lot more helium than we thought we should be using based on the number of instruments and the typical operating conditions in our building. So the Agilent GC division, the people who maintain our site, went on a search with leak detectors and found a number of leaks, also infrastructure tubing and things like that that were getting old and needed to be changed and upgraded. And by fixing these infrastructure problems, we were actually able to reduce our helium consumption by 50%. So this is actually a huge improvement with the use of helium in the building, and probably represents the major impact that you can have in your facility. Another approach that I've seen taken by some customers is actually turn off the system during idle time so it's not running at all. Everything is cooled down and physically turned off. However, this really isn't recommended for many GCs and really not recommended for GCMS because of the need to maintain vacuum in the mass spectrometer. Turning the system off and cooling it down is really bad for a number of GC columns and traps. Air can diffuse into the columns, causing oxidation, and a lot of the traps or specialty pack columns that are used in some industries are damaged by air and by heating and cooling by turning the system on and off. So we want to try to avoid that, and that's not really the best approach to conserving helium. So if you fixed all your infrastructure issues and you want to now try to minimize the amount of helium being used by your methods, we're going to provide a solution for that with a helium conservation module for the gas chromatograph. We actually introduced for the 7890 GC a number of years ago, the first generation helium conservation module, and this was based on a standard 3-channel aux EPC system that was modified to be able to conserve helium and to switch to nitrogen as a standby gas during idle time. Since the introduction of the 8890 and the 8860, we have improved and updated that to the next generation or second generation helium conservation module to work with our new GC platforms. The way this works is it automatically switches the carrier gas supply in the instrument to nitrogen during standby time or idle time of the instrument. So when you're not actually collecting data, the helium is turned off and nitrogen is automatically substituted for that. It maintains an inert flow path. You can keep everything hot. And this will save a lot of helium in your system. We can also automate that with our OpenLab CDS data systems because we have sleep and awake methods that are standardized in the instruments and in the CDS. So the sleep method would be one where nitrogen is used during idle times, and the awake method is where you would switch back from nitrogen to helium with an awake method that would bring everything back up to operating condition and then purge out the nitrogen that was used for the sleep period with helium. Now we can combine this with gas saver mode that has been built into Agilent's GCs since the 6890 days, and these gas saver mode combined with the helium conservation module will give you the greatest reduction in helium consumption. So gas saver mode is used with our GC inlets, particularly our splitless or multi-mode inlet. And what this will do is for high split flow methods, you'll have that initial high split flow of helium during the time of injection, and then after the sample has passed from the inlet to the column and the split has been achieved, then the split flow is reduced to a maintenance level at a lower flow rate to save helium. So let's take a look at the next generation of helium conservation module and see how it's configured and how it actually works. So I'm showing here are two configuration examples. Now you can think of the helium conservation module as a programmable gas delivery middleman that's built into the 8890 or the 8860. So the helium conservation module is just another type of EPC. So it's put into the back of the GC with the other EPC units. However, we don't plug our carrier gas now to the other EPCs. We simply plug the supply line of the helium into the helium conservation module, and then we also plumb into that a nitrogen supply. So those are the two inlets into the helium conservation module, either both helium and nitrogen, and then there's one common outlet, and this is what's used to deliver the appropriate gas to the various other EPC modules in the system. So on the left-hand diagram, we're looking at the back of the instrument. We can see our helium conservation module. So the outlet goes up to a T, and that T is plumbed to our front inlet EPC and to the back inlet EPC. So now the helium conservation module will then change the carrier gas supply to both of those inlet modules. On the right-hand diagram, it's a slightly more complicated plumbing. So again, we have our helium conservation module where our two carrier gas supplies come in. Then we have our common outlet. And then rather going to a T, we're going to a cross. So this is going to deliver the appropriate carrier gas when needed, either helium or nitrogen, to both the front and the back inlet EPCs. And then if you have an auxiliary EPC module like a pneumatic switching device or PSD or an aux EPC or a PCM, these auxiliary flows are often used as secondary flows for valve operations or for fluidic switches. So the conservation module would also be used to deliver carrier gas to those auxiliary systems. Now we've seen how the helium conservation switch is plumbed and set up in the 8890 or 8860 GC, let's take a look at how it operates in the sleep mode and in the wake mode. In the sleep mode, the channel controlling helium is turned off. So this stops delivery of helium to the other EPC modules plumbed to the helium conservation switch. At the same time, the EPC channel that has nitrogen plumbed to it is turned on, and nitrogen will flow from the switch to those other EPC modules. In this mode, helium is being conserved while nitrogen is being used to maintain an inert atmosphere throughout the GC. In the right-hand diagram, the opposite is happening. This is in the wake mode. So now the nitrogen is turned off and the helium is turned on. So this allows helium to then flow through the module and then be delivered to the various EPCs. There's another channel that I didn't initially discuss, and that's the third channel in the helium conservation switch, and this is the purge channel. The purge channel serves an important function, particularly when going from the sleep mode or nitrogen mode to the helium mode. In the helium mode, the purge channel allows helium to purge out all the nitrogen that has been accumulated in the module so that it doesn't leak through and go to the other EPCs. We want to make sure this doesn't happen because nitrogen can respond to some detectors like a mass spec or a TCD. We want to make sure that there is no residual nitrogen in the system. So this is typically how we will use the helium conservation switch to reduce our helium consumption while still allowing the instruments to be turned on and hot during the course of our operations. So now after we switch from our sleep to our wake mode, where we're going from nitrogen to helium as the carrier gas, the question becomes how long does it take for all that nitrogen in the system to purge out so that we're actually ready to operate our GC to do sample analysis. And so we've done a study with using a mass spectrometer, and we found that going from the sleep to the wake mode, if we wait 15 minutes in the wake mode, this will allow the helium to remove all the residual nitrogen throughout the entire flow path and get back to an operating level of nitrogen with helium carrier gas. So we see here in the mass spectrometer, within 15 minutes, we're now down to a low enough nitrogen level that we're able to pass the auto tune. If you're using, for instance, a TCD, it actually takes a little bit longer because the TCD is very sensitive to nitrogen. And so I would recommend waiting for between 30 minutes and 60 minutes of purge with the helium to remove all of the nitrogen. Now, as I mentioned, we can combine our sleep and wake methodologies that are built into our GCs and our data systems to actually set up a program to put the system in the sleep mode when we want to go idle and use nitrogen as the carrier gas, and then to automatically turn on, say, an hour or so before we come into the laboratory to go into the wake mode to purge out the nitrogen with helium and assure that we're ready to run when we get to the laboratory. And this can be set up in a program way, much like a thermostat in your house can be programmed. So I know in our house we have a thermostat, and during the day when we're not home, I have a program to let the house temperature cool down to save on energy for heating the house. And then a half hour or so before we come home, the thermostat automatically turns on and then warms the house up. And then opposite in the summertime with heating and cooling. So the same thing can be done with the sleep wake mode. You have a program built into the system, the CDS, or to the firmware in the instrument to set sleep and wake times to invoke those two methods. So you can set this up in a very simple and straightforward mode to automate going from the sleep and wake cycles. Okay, so the question now becomes, how much helium can I save using the helium conservation switch and the sleep-wake methods that I've just described? There's really no one answer for this. It really depends on the method that you're running, so how much carrier gas the method uses, then also how often you're running that method during the day. So we put together a helium savings calculator, and what this allows us to do is put in the operating conditions for a particular method, and then also the size of gas cylinders that we're using if we're delivering our gas to the instrument with cylinders, and then also what the cost of the cylinder cost is, and for using the nitrogen mode, the nitrogen cost. So you can see it with this calculator. If we're not doing anything, there's no conservation. Using this ASTM method, D4815, which measures oxygenates in gasoline. This is a two-dimensional GC method, so there's actually auxiliary flow in this method as well. You can see that with no conservation, a typical cylinder will last about 71 days. And so the yearly costs for operating this method for basically one shift a day is about $1,537 using the helium costs that we're currently invoking at our laboratory. Now, if you use the conservation switch along with the gas saver mode, you can see that we can reduce that from helium use will go from 71 days, and we can extend the lifetime of the cylinder to over a year. And this will reduce our yearly cost to about $356. So the methods that get the best bang for the buck with this is methods that use a split flow and high flows, and then also those that are run not 24/7, but through a normal workday, and maybe not over the weekend or overnight. Okay, so what happens after we switch from nitrogen in the sleep mode going into helium in our run mode? Are there any effects on the chromatography going back and forth between the sleep and wake cycles? So in this case, I'm showing just some chromatography. So in the upper chromatogram is my reference run. So this is the original analysis using helium carrier gas that's run during the day. And then overnight, we go into the sleep mode where we're substituting nitrogen, allowing the system to be idle with nitrogen flowing. And then we use the wake cycle to switch back to helium, let it purge out for about a half an hour. And then we do our first run of the day, and we can see that the chromatography hasn't changed at all. So there really is no effect going from the sleep and wake cycles, as long as you've purged out the nitrogen for an appropriate amount of time. Then finally, we also see for the third day, again, there's no change in the chromatography. So this helium conservation approach, what are the benefits? The greatest impact, as I said, is with split methods and for GC systems that are not running 24/7. It's also an advantage where you're not changing anything in your methods. So if you can't change the methods or you don't want to revalidate them with an alternative carrier gas, the helium conservation approach is probably the best way to reduce helium consumption. Also, if you use a lot of GCMS methods, those are best run with helium, and so the helium conservation switch and helium conservation approaches will give you the optimum performance when needed because you don't have to change the carrier gas. Okay, so we've discussed in some detail helium conservation and some of the ways to best use your helium resources if you don't want to change carrier gases. However, if you do have the option of changing the carrier gas, what are the best approaches to alternatives? So it will depend on whether the instrument is a GC or GCMS. If you're GCMS, your real choice for an alternative is only hydrogen. Nitrogen can't be used. It really is not appropriate for mass spec because it just reduces the sensitivity for the mass spec to the point of it being useless. However, if you're using GC methods, you do have more options for carrier gas, not only nitrogen, but there are others, but nitrogen is being the most common. If your resolution is really sufficient, you have high resolution, then you could switch to a nitrogen carrier gas and give up some of the resolution that you would typically get with helium or with hydrogen. Nitrogen will be perfectly suitable for that. If you are resolution critical, however, your only real choice for GC methods would be to consider migrating to hydrogen carrier gas. So we're going to discuss some of the considerations for both using hydrogen and nitrogen as helium alternatives. Because before we get into that, let's just take a look at these two tables. These are our various carrier gases used with various detectors. The most common carrier gases besides helium, hydrogen, nitrogen, argon, argon, methane, hydrogen and nitrogen being the most common. Your detector that you're using can influence your choice. So for instance, if you are using a thermal conductivity detector, oftentimes nitrogen is not the best choice because it has a high thermal conductivity and it will reduce the sensitivity looking for things like hydrocarbons or other fixed gases. However, if you are using a TCD to measure hydrogen or helium, then nitrogen actually represents a good choice because there's a large difference in thermal conductivity. But that's kind of a corner case. So I'm just providing this for reference. Let's move on. Now, when considering conversion from helium to hydrogen carrier gas, there are a number of aspects of our methods that we have to take into account. In general, methods require less optimization when going to hydrogen carrier gas if the analytes are durable. Hydrogen is a reactive gas, it's a reducing gas, so those compounds that won't react with hydrogen are best suited. Also, compounds that are at higher concentrations are also more suitable when using hydrogen carrier gas, particularly with a mass spectrometer. In general, hydrogen carrier gas will offer a little less sensitivity than helium with mass spectrometers. Also, in general, analytes that are used with split injections are more suitable with hydrogen carrier gas, particularly if those are more reactive. And that's because with split injections, the residence time of the injection is lower inside the inlet, and so there's less of a chance of reaction with hydrogen carrier gas with split injections. Also, compounds that have been derivatized to improve their gas chromatographic performance will also be better suited for hydrogen. And that's because the functional groups that are reactive, that cause poor chromatographic performance, have been derivatized to make them better chromatographic compounds. And those active sites have been masked by the derivatization compound, so they won't react with the hydrogen. Methods that will generally require more optimization are, of course, the opposite. Any fragile compounds will first have to be evaluated with hydrogen to make sure that they aren't changed or lost in the presence of hydrogen. Also, if you're looking at the absolute lowest trace level concentrations, you'll have to validate your method with hydrogen first that you can achieve those because, as I said, in general, hydrogen is a less sensitive carrier gas, particularly for mass spec operations. Before you complete your change from helium to hydrogen, you also have to allow the necessary time to update any SOPs and method validation with the change in the carrier gas. Now, some considerations when switching to hydrogen. You have to be aware of the flow limitations due to the mass spec pumping capacity. Oftentimes, hydrogen is run at higher flows because you get better performance, chromatographic performance. So if you're going to use those higher flows, you have to make sure that your mass spec has an adequate pumping system like a turbo pump rather than a diffusion pump to accommodate that higher flow. Also, there can be changes in peak elution order with the carrier gas, so you will have to revalidate those peaks, making sure they're identified properly. And then you'll also have to consider the column sample capacity because that can change with the use of a different carrier gas. As I said, hydrogen is not an inert gas, it's a reducing gas, so it can react with the compounds that you're trying to measure. So you also need to consider the full inert flow path, and we generally recommend to use inert columns. We have ultra-inert columns and ultra-inert flow paths that may be more appropriate with hydrogen carrier gas. You also want to use the lowest temperatures possible. This is particularly true of your inlets and, for instance, transfer lines with the mass spec. Again, higher temperatures will cause hydrogen to be more reactive. And then most importantly is you want to avoid some solvents, particularly using splitless injections and hydrogen carrier gas. So those would be methylene chloride, carbon disulfide. That's because they have a long residence time and a high concentration in the inlet at the time of injection, and they will react with the hydrogen, and they'll cause the formation of hydrochloric acid and also sulfuric acid, and that will cause definite maintenance issues with the inlet and poor performance of the system. Now, before switching, particularly those of you who have older mass specs, the 5977 series is okay. Those are completely proven for hydrogen use. Some of the older 5975 systems, however, do have source magnets that are not compatible with hydrogen. And the way you can tell that is you look at the magnet, and if it has a serial number on it, then it is compatible with hydrogen carrier gas. If it does not have one, do not use hydrogen. If you do want to use it, contact your Agilent service engineer, and there is a magnet that can be swapped out that will allow you to use hydrogen. Also in the source, we have lenses that are optimized for better hydrogen use, and those are shown here. So on the left is the standard 3mm draw-out plate. That one is not the best for hydrogen. We have a 6mm draw-out plate, and then also now a 9mm draw-out plate that's been introduced for our various sources. Those are better used for hydrogen carrier gas, so we would recommend converting that source lens when transferring from helium to hydrogen. Now, when converting from helium to hydrogen, one really can't expect to immediately start running samples just by replumbing the carrier gas into the instrument. There is going to be some initial setup and some performance expectations that will have to be dealt with. So after the switch to hydrogen, you'll notice initially that there's going to be a high background on your GCMS signal when using a mass spectrometer. If you look at the spectra of this background, it will look like hydrocarbons. So there is going to be a startup procedure that I'll discuss in a minute or so for cleaning out this background and getting the contamination removed as much as possible from the system. There's also going to be a reduced signal to noise with hydrogen carrier gas, and that's because helium will give the best signal to noise, but because of the ionization and the size of the hydrogen compared to helium, you're not going to get as efficient ionization, and so your minimal detector limits will be lower. And then finally, until the system is conditioned, you're going to see significant tailing if you don't do that conditioning. And in the right-hand chromatogram, you can see that in this case, there's some drugs of abuse that show extreme tailing, and particularly the cocaine peak. So this is going to require some initial startup to try to minimize these effects. Now, for any GC or GCMS system, there is going to be an initial setup and a calibration time when switching from helium to hydrogen carrier gas. And for GCMS, I'm listing some of those steps here. So after you plumb in your hydrogen carrier gas to your GC, you're going to allow the system to set up overnight to clean using the hydrogen carrier gas. So after doing the plumbing, you'll pump down the system. You'll set your source temperature to the maximum temperature for your particular source, depending on the mass spec that you're using. At the same time, you're going to reduce your electron multiplier voltage down to 800 volts. Then you're going to run the system overnight with the filaments turned on. And what this will do is this will ionize the hydrogen coming into the source, and this will allow the system to be cleaned. So you're going to run this overnight, and then the next day come in and do a matrix check to be sure that everything looks okay. If it looks okay, then you're ready to go. So this shows the checkout after doing the overnight cleanup with hydrogen. And so we're going to compare the results with the helium run. So after conversion from helium to hydrogen, we can see the chromatography here. There is still somewhat some tailing that can be expected depending on the compounds. Other compounds may not tail at all. So you can see, for instance, that large peak at about 7.5 minutes. There's not very much tailing at all. And in fact, the response in hydrogen seems to be better than in helium. However, some of the other peaks are showing some tailing and some reduced response, and that's just the nature of using hydrogen with a GCMS system. So after conversion from helium to hydrogen, what can you expect in your analytical results on a GCMS system? First, the sensitivity can potentially be reduced on the order of 2 to 5 times reduction in sensitivity. Again, hydrogen is a larger molecule and it's easier to ionize it than helium, and so that is going to reduce some of the sensitivity in the source. Some trace reactive compounds may be lost, and you may not see them at all. And then also you can see that there could be changes in the actual mass spectra or the spectral fidelity. So there could be some changes in the observed ion ratios for some compounds. And there also could be missing or extra ions. And this will actually affect your library searching. So in this example, we show lindane, and you can see that in the upper chromatogram with helium, the lower mass ions are somewhat reduced. However, if we look in the hydrogen carrier gas, we're getting larger response for those lower molecular weight ions. And so this will affect the search. So you can see in the helium carrier gas, the search quality was 925, but with hydrogen, it's been reduced somewhat to 859. And then in the table on the right, this is a number of different pesticides. And you can see that the difference in this library match between helium and hydrogen does show somewhat of a difference. And you'll have to be prepared for that when evaluating your result. Now, before getting into the details of converting methods from helium to hydrogen, I'm first going to have to discuss some hydrogen safety features that are built into the instrument, and then also some best practices for making the use of hydrogen as safe as possible. We can provide for all of our Agilent GCs a letter from Agilent Safety Engineer that describes the built-in features for our instruments for using hydrogen in the safest possible manner. These are available for our latest instruments, the 8890, 8860, and also the Intuvo GC. In this slide, we show some of the safety features that are built into our instruments that are described in the letters. First of all, we have a safety shutdown. So whenever the gas pressure set points are not met, so this would be the cause of a leak or a broken column, the valve and the heater are shut off. So the valve turns off the hydrogen delivered from the EPCs to the instruments. And then the heaters are also simultaneously shut off. And this prevents any possible explosions that could take place with buildup of hydrogen in the instrument. We also have built into all of our EPCs that are hydrogen compatible a flow limiting frit. So if the valve fails in any way and stays in the open position, these frits minimize the amount of hydrogen that can be delivered through the EPC and into the instrument. Also, in our on-off sequence for the oven, before the heaters are turned on, when turning the instrument on, the fan will come on and will purge the oven with multiple volumes of exchange of the internal gas chromatography oven to remove any collected hydrogen. Only after this has been run for a few minutes, then the heaters will be turned on. And then finally, we also do some rigorous explosion tests for all our instruments, where we put into the inside of the instrument a lower explosive limit of hydrogen. We ignite that hydrogen, and then we make sure that if there is an internal explosion, that no pieces come off of the instrument to be projectiles that could hurt or injure any laboratory personnel that are near the instrument at the time of an explosion. As a second level of safety, we also offer an optional hydrogen sensor module. This goes into the back of the GC. It's available for a number of our more modern instruments. So I show a picture of it here. It's a board that goes into the back of the GC. And on the board is a long probe that comes through the back of the instrument and into the actual column oven. And this is a sniffer port. So this actually draws the atmospheric gas inside the oven into the module, or the hydrogen sensor module, and measures the amount of hydrogen that can be detected. So the way this works is we install that in the instrument, and then there's also comes with a lecture bottle of some hydrogen that's at about 1% hydrogen in an inert gas. This can be used to calibrate the sensor, and you can also set up how often the sensor becomes calibrated. So this is available for our most modern instruments, our current instruments, the 8890 and the 8860, and then also for some of the older instruments, the 7890A plus. So if you have 7890As, you could get this if you upgrade it to an A plus. And then all the 7890Bs are also compatible with the hydrogen sensor module. Sources of hydrogen can be varied. We prefer, or what we recommend, are hydrogen generators. We show the Parker hydrogen generator here. This generates hydrogen by filling it with water, and it hydrolyzes the water to convert it to oxygen and hydrogen, and then we'll deliver that to your gas chromatograph. And you can get these in various sizes to accommodate different maximum flows of hydrogen that are required for multiple instruments. For hydrogen cylinder delivery, we recommend a clean gas filter. There are third-party devices that can be added to the plumbing outside of the GC that will shut off the cylinders if there is a loss of pressure or if a leak is detected. We don't sell those, but the environmental health and safety officers for most companies know where to acquire these. For many laboratories, hydrogen is delivered from a common source throughout the building. And so, of course, the local building maintenance people and environmental health and safety people typically do a routine hydrogen safety check. Now, when plumbing your GC to whatever hydrogen source you're using, we're recommending to use really good quality stainless steel tubing. We also say don't use older tubing. These can be contaminated just by sitting around the laboratory, and hydrogen is known as a scrubbing gas, and what you'll see is a high background. So use new stainless steel tubing or tubing that's been thermally cleaned. We don't recommend using copper tubing, especially old copper tubing. Copper does become brittle over time. There's also some indication that hydrogen flowing through copper tubing accelerates the brittleness, and so this can cause breaks in the tubing and leaks and delivery of hydrogen where you don't want it. For your split vents, you want to make sure that your split vents are connected to an exhaust, because you are going to be putting sometimes high flows of hydrogen out into the laboratory atmosphere, so you don't want to let those set off any alarms. And then also, when you're plumbing up a new system or making any changes to your instrument, you want to be sure that you check for leaks. We don't really recommend Snoop, especially because it is a surfactant, and if that gets into your flow path, it can cause contamination problems. So we really do recommend using a leak checker. We have one. They are more expensive, but they work extremely well, and they're very good for detecting hydrogen leaks. Now, when converting methods from helium to an alternative carrier gas, These are just some bullet points here. We want to make sure we follow all the safety protocols and recommendations for your facility. So you want to start when converting from helium to an alternative, you want to start with an existing helium method. It's easier than trying to create an entirely new method with a new carrier gas. Then we provide a software tool called method translation software to help you make that transition to the alternative carrier gas from an existing helium method. So the method translation software assumes that you're using the same column, both the column phase and the dimensions of the column. And then when you do your conversion from helium to hydrogen or even to nitrogen, the method translation software will be assured that you have the same peak order and retention time for your new operating conditions with the alternative carrier gas. So after you do that conversion, you want to make sure that you use the software to check to make sure your GC can meet the new method conditions, for instance, column head pressure. And then also when you're translating a hydrogen method, once you validate that, then you want to only then go through and explore some possible speed improvements, because hydrogen carrier gas does typically work at its optimum mode at higher flows than helium, and so you could potentially get an improvement in speed for your methods without any loss of resolution. Now, as an example of using the method translation software, I'm showing it here with a ASTM method, D5769. This method is a GCMS method that is used to measure aromatics in gasoline. So I'm interested in taking my helium 5769 method and converting it to hydrogen. So in this case, I'm showing a screenshot of the method translation software. So under the original method parameters, we enter in all the column dimensions of the flow that we're using and the temperature program. And then in the calculated method parameters, we make sure that the column dimensions are maintained. They're the same as the original method. And then we go over to the speed gain in the upper left-hand corner. And for a simple conversion, we're going to do a speed gain of 1. So this will make sure that the retention times and the peak elution order, once we convert to hydrogen, are maintained. And then finally, we go over into our calculated method and we make sure that hydrogen is selected. What the method translation software will do is it will then calculate a new head pressure and a new flow for the instrument using the hydrogen carrier gas. So we do maintain our peak elution order and retention times. So we can see the effective translation of 5769. So in the upper chromatogram, I have my helium carrier gas. This is a calibration standard. And if we look at the retention times, we can see that the run goes from, with peaks from about 6 minutes out to just under 30 minutes. Then after I've used the method translation software to go from helium to hydrogen, you can see that there's almost no change in retention time, a very minimal change in the retention times. And then also the resolution, well, it's about the same, and there's no changing of the peak elution order. And so what this allows us to do is have minimal changes to the method because we're measuring all these compounds. We want to make sure that our integration parameters and our peak identification and peak quantification parameters remain the same. And so this will help with setting up the method for going from helium to hydrogen carrier gas. And then this is an example of after the conversion running a sample. So this is an actual gasoline sample that was used in a proficiency testing program. So the upper chromatogram shows the helium carrier result, and the bottom shows the hydrogen carrier result. You can see that pretty much they look the same. The hydrogen looks a little busier, but if we look at the results, and that's shown in this slide, the results between the helium and the hydrogen carrier gas are nearly identical. So for our benzene, toluene result, 0.23 volume percent of benzene, 0.39 for helium, and pretty much the same for hydrogen carrier gas. For the total aromatics, we have about 19.65 with helium and 19.68 for hydrogen. And those match well with the consensus values that other laboratories have determined for this particular sample. Now, of course, besides helium and hydrogen, nitrogen is another carrier gas that can be used and serves as a potentially good alternative to helium if we're trying to save helium. A number of methods that are used in chemical and energy, or what we used to call hydrocarbon processing industry, are well suited to nitrogen. Things like simulated distillation, where absolute resolution isn't required. Nitrogen may be a very good choice as an alternative to helium. Some of the advantages of nitrogen: it's readily available and it's less expensive. So you can find it in good chromatographic grades pretty much anywhere in the world. Aside from using pressurized gas cylinders, there's no other safety concerns with nitrogen as there would be with hydrogen, because it's not a reactive or explosive gas. It's really very suitable for simple routine analysis where you have more than enough resolution. And then nitrogen is also suitable for some 2D GC techniques. These would be where we're using two different columns to optimize resolution. So we're using the column to give us the best resolution, and so the nitrogen may be a good carrier gas for this. These are typically for packed columns using valves, where we're using multiple columns and valves to tweak a separation. However, for the more sophisticated 2D techniques like GC-GC, nitrogen is not really a suitable carrier gas. Some potential issues for nitrogen: there are reduced chromatographic resolution at higher flows, at the flows that we're typically used to using with helium. So you won't get the same resolution. And again, it can't really be used with GCMS and some other GC detectors because of loss of sensitivity. So when trying to convert from helium to an alternative carrier gas, we're going to take an easy approach. As I described earlier, we're going to take an existing helium method, and we can use some of the firmware in the GC system to make this conversion easy, even without using method translation software. So the goal here is to change the carrier gas while keeping all the other method conditions exactly the same. So we're going to use the same column, the same oven program, and we're going to adjust the flow or the holdup time so that we maintain the same peak elution order and keep the retention times of the peaks as close to the original value with the alternative carrier gas as we observed with helium carrier gas. This makes validation easier because there's minimum changes to integration events and also the peak identification tables if the elution order and the retention times don't change significantly with a change in carrier gas. If you're using a nitrogen as the alternative, you do want to test the resolution of key components. Make sure that those are still sufficient enough to be able to separate and quantify those components. And we can use the tools directly built into the firmware or into our chromatography data systems to guide through the process. Now I'm showing here the Van Deemter curve, and I'm going to specifically be talking about nitrogen as it relates to the Van Deemter. So I'm calling it the tyranny of Van Deemter from a nitrogen standpoint. We've done a very good job over the last 40 or 50 years with capillary chromatographers of convincing them that nitrogen is not an appropriate gas for capillary GC. And we use the Van Deemter curve to do that. So in this case, we're doing a separation. We can see here on the right of a couple of components with nitrogen, helium, and hydrogen all operating at a linear velocity of about 58 centimeters per second with the corresponding flows shown here. And then what we are measuring is the resolution. And if you look at this, you'd say, oh, well, nitrogen is a terrible carrier gas because it doesn't provide any resolution at all. However, we're looking at it, the nitrogen at a high flow rate. If you actually look at the Van Deemter curve, nitrogen potentially is the best carrier gas for resolution. And that's because what we're looking for is to try to maintain our system at the minimum of the Van Deemter curve, where the efficiency is the best. And you can see that nitrogen actually has a lower height equivalent of the theoretical plate, and so this has the best resolution, potentially the best resolution, and the best efficiency. Unfortunately, that happens at a lower speed. You can see the linear velocity where this occurs is somewhere around 10 centimeters a second. So what happens is people don't really consider nitrogen because they don't want to wait for 2 or 3 times longer to get their results. However, most GCs use constant flow mode, and so with changes in flow due to changes in temperature, those are not observed as they were in the past before programmable EPCs. Okay, so to demonstrate converting a helium method to nitrogen or to hydrogen using the simplest process possible, I'm looking here at a test case. This is again another ASTM method. It's D6584. It's used to measure contaminants in biodiesel, specifically mono, di, and triglycerides, and also glycerol. So I'm showing the instrument conditions here. So the ASTM method uses helium carrier gas at 3 mils a minute, and it's run in the constant pressure mode at about 7.63 psi on the inlet. And this just shows the region where the peaks of interest are eluting. Now, the first step when changing from helium to either hydrogen or nitrogen is, of course, to plumb the carrier gas to the instrument. Then we have to tell the instrument that we have made a carrier gas change. So to do this, you go into the configuration screen for your particular GC, go to the inlet where you've changed the carrier gas, and select the appropriate gas. So in this case, we have a cool-on column inlet that we're going to change, and we go from helium to hydrogen or nitrogen. After making that change, go over and look at the column section and look at the flow. So as I said, this method uses 3 mils a minute of flow, but we also want to look at the hold-up time. So with helium carrier gas, the hold-up time is 0.47 minutes at a 3 mil a minute flow. So do I want to maintain the same flow with my alternative carrier gas, or do I want to maintain the same hold-up time? Let's see what the difference is. So in this case, I'm showing the same run. We're going to be looking here at the monoglyceride elution area. And this shows in the upper chromatogram helium at a flow of 3 mils a minute. This is the 7.63 psi, and the hold-up time is 0.47. Now, if I maintain the same flow with hydrogen or with nitrogen, you can see that the flows are the same, but the hold-up times are different. So for hydrogen, the hold-up time is now 0.42, which is a little faster. And then for nitrogen, it is 0.46, which again is faster still. And you can see that result here is that the hydrogen peaks are eluting faster than the helium. And then in nitrogen, they're eluting a little bit faster than the helium, but not quite as fast as the hydrogen. But the point to note here is the peaks are not at the same retention time. And what we really want to do is maintain them as close to the original retention time as helium as possible. So instead of maintaining the same flow when changing carrier gas, let's maintain the same hold-up time. So in this slide, we're looking at the hold-up time is being maintained with the different carrier gases. So it's the 0.472 minutes, and you can see now the peaks line up much better. And so this will save us from having to do a lot of changes to integration parameters and to the calibration table for quantifying these peaks. Now let's take a look at some of the resolution. And you'll note that in the hydrogen, some of the peaks have better resolution. So those eluting at about roughly 18.5 minutes, you can see that the resolution for those two pairs that aren't quite baseline resolved are better with hydrogen. But if we look at nitrogen, you can see that the resolution is entirely lost. And so in this case, if we were interested in maintaining that resolution, then nitrogen would not be the best carrier gas of choice as an alternative. Hydrogen would be. Now, if we look at what we're actually doing with this analysis is we're reporting as an aggregate the monoglycerides. So in this case, the resolution of that pair is not really important, is because we integrate them and report them together. So in this example, we could use nitrogen as a carrier gas because even though we've lost resolution, it doesn't really affect the overall results because we would have integrated those together anyway, and we're not really looking for complete resolution. And again, this has to be a judgment that you make. Is the carrier gas delivering for you the resolution that's required by your analysis? So those results are shown here. So no matter what carrier gas we use, we're getting the same result for all of our different classes of compounds with this sample. So in this case, I would say either hydrogen or nitrogen would be an appropriate carrier gas to use for this particular method, because this doesn't really affect the overall results and the chromatography required by this method. So in summary, I've shown that we can easily migrate your GC method conditions from a helium carrier gas. So for methods where resolution is absolutely critical, hydrogen will offer the best alternative. And also for GCMS methods, hydrogen will be the best alternative. For many GC applications, nitrogen can be used. It offers a cheap and easy alternative without the safety worries that can sometimes accompany hydrogen. Most existing helium methods do have too much resolution, so a change in nitrogen, even at the same analysis speeds, generally won't affect that if, again, you have sufficient resolution. Nitrogen can be used without changing any of the existing GC conditions, as long as you keep the hold-up time the same and not try to match the flow. And then 2D methods, particularly those with PACOMs and valves, are ideally suited to nitrogen. However, GC or comprehensive GC are not really suited for nitrogen. And then, as I discussed at the top of the presentation, if helium alternative is not an option, if you really don't want to change to another carrier gas because you don't want to change your SOPs or have to revalidate your methods, we do offer an approach to using helium with the conservation features built into the instrument. So you can combine the gas saver mode for your splitless or MMI inlets with the new second generation helium conservation switch. And potentially this can save you up to 10 times in helium costs, again, depending on the operating conditions and how many samples you're running with your instrument during the day. So with that, I'd like to thank you for participating in our seminar. I hope you found this information useful and interesting, and I hope to see you again at some other Agilent presentations. And again, thanks for participating from Agilent Technologies.